the antenna group webinar. So without further ado, we've only got a short time slot, so I'm going to kick in and ask the first speaker to present. That's Akram Alamani.
Hello, good morning, everyone. I hope you can see my slides. So thank you, Clive, for the introduction, and thank you to all the attendees. So my name is Akram Alamani. I'm a reader in Antennas and Applied EM at the Antennas Electromagnetics Research Group. So today, briefly, I'll talk about some of the research we do on using or exploring the potentials of EM waves from body scale to nano communication for healthcare application. So healthcare has gone through a large transformation, and with the vision of having everything remotely and diagnosis happen at the fingertips, to having wearables and devices printed on our skins, on our clothes, and being integrated with our daily activity to be able to collect data continuously. However, there are so many challenges related to that. And one of the most or the largest motivation to move forward with working in this area is the cost that the burden on the National Health Services and increasing cost of healthcare, whether it is as hospital, primary care, or even at home. So the idea of how can you move this further and provide a solution that will enable you to be able to quantify yourself efficiently, enable to exchange data with certain hubs and care providers, and enable you to give the feedback that is both useful from the patient perspective and also for the National Health Service, where they reduce the cost significantly. So some of the activity we've been working on in the group is with the School of Medicine and Dentistry at Queen Mary and some of our external partners as well. One of the areas we're currently working on is localization of wireless endoscope devices within a colon. And this is important when it comes to colonoscopy and also for bowel cancer research, where consultants and carers, they need to make sure that they identify the source of, for example, an infection or an ulcer that could cause and progress further on. This kind of technology will allow you to monitor a specific area and also get or collect information on the progress of whether it is an inflammation or infection that could turn at a later stage into a cancerous or harmful object. So this involves innovation in antennas, in algorithms, in machine learning to be able to track the capsule within an accuracy of a sub-centimeter, which is very important for the consultants. And then in addition to that, some of our work has been historically on body-centric networks and wireless sensor networks. And recently we have moved into the nanoscale and looking at perspective of how can we apply some of the conventional communication and networking concept at the nanoscale. Does everything just scale down, or it needs innovation in terms of understanding the channel? One important aspect we face here when you move into very high frequencies to deal with nanoscale is that, for example, a 1 millimeter layer of a skin or a tissue, it doesn't become a continuous or a continuum medium. So we need to understand it in details. So some of our work has been on identifying an accurate 2D or 3D EM modeling of biological samples. This is again working with the medical school, with Cutaneous Research Group at Queen Mary, and trying to identify how can we numerically model these skin samples with a progression from a time and a space perspective. How do they vary, the electric properties? How does that influence the communication channel? And ultimately, how does it influence a monitoring or diagnostic tools that could be embedded within human tissues and the human body, exchanging information with carers and external sources? And all this actually encompasses under the umbrella of innovation in antennas, compact antennas, embedded antennas, implantable, and also radio channel propagation and characterization. And this also forms a part of what we call wearable creativity at Queen Mary, where we have a number of people from different disciplines working on solutions where you can actually have this wireless communication, this quantified self-communication as a seamless experience. And I think that's my time here. And yeah, I'm waiting for a quick question towards the end of the session. Thank you.
Thanks, Akram. Our next speaker is James Kelly.
Okay, so my name is James Kelly, and I'm going to present to you today about reconfigurable antennas based on liquid metal. And I want to talk to you about some of the things that we've been doing. For several decades, there's been research on the topic of reconfigurable antennas and circuits. And one of the most popular techniques that has arisen for this is to use semiconductor devices such as switches and tuning elements like varactors. That technology is quite mature, but it suffers from some important limitations. So one of those limitations, as we see it, is that the semiconductor switch or varactor has a complex input impedance, which varies as a function of frequency. And that makes the design complicated, more complicated. Also, the switching or tuning element has significant power consumption. And also, because it has a junction, it adds to harmonic distortion. Finally, the overall circuit or antenna has limited tuning range. Now, around 2014, interest started to grow in using alloys of gallium to try and address that problem. And the alloy that I'm talking about is actually commercially available, and it has excellent properties which address most of those limitations I mentioned earlier. In Queen Mary, we've looked at a range of different reconfigurable antennas and circuits and tried to demonstrate different things. So we've, for example, demonstrated how we can expand or contract 2D areas of liquid metal, and in that way we've developed a frequency reconfigurable antenna. We've also shown how it's possible to add or remove sections of ground plane from an antenna, and in that way demonstrated a bandwidth reconfigurable antenna. We've added and removed parasitics from an antenna, and that way demonstrated beam steering. And finally, we've shown how it's possible to add or remove vias from a substrate integrated waveguide structure. And in that way, we've demonstrated the ability to add or remove walls from a structure or add or remove reactive loading. And that's led to development of switches or phase shifters. So that concludes my presentation.
Thanks very much, James. Our next speaker is Rob Donnelly.
Hello, I'm Rob Donnelly, and I'll talk about doing biophysics with antenna transceiver systems. The Antennas and Electromagnetics Group extended their 50 years long-standing metrology activity into the terahertz band of the electromagnetic spectrum in 2009. Now, the terahertz band occupies the interval between the upper edge of the microwave and the lower end of the infrared. It's a band of the electromagnetic spectrum that was largely inaccessible to coherent transmission and reception until the early 2000s, and that came with the advanced development in vector network analysis, and there the baseband has continued to increase, and it can be extended into sub-terahertz and terahertz frequencies with frequency multiplier heads. And also coherent transmission and detection at terahertz can be done with the time domain spectrometer. We use both of these systems to observe and understand physical phenomena that uniquely occur in the terahertz, and so we directly measure a variety of normal modes, whether phonon modes or intermolecular vibrations. We've applied the VNA and the time domain spectrometer to do circular dichromosome spectroscopy, and that's been recently reported in an IEEE transactions paper where we modeled a system of myoglobin, which is a structure that's taken to be a model system, and it was studied using this quasi-optical breadboard that was driven by a vector network analyzer. The importance of this research is that we're looking to provide a redress to the poor reproducibility of measurements. That is a handbrake on much work that's done in structural and condensed matter physics. What we want to do is to provide measurement traceability, and particularly to the recently redefined definitions of length and mass. And this is done in collaboration with the National Physical Laboratory. The significance of this is that it makes realistic, for example, the ambition for efficient and targeted yield of a drug product, because you can observe and steer the reaction coordinate, where a lot of the important information is happening at terahertz frequencies directly. And once you overcome the water problem, which is common for terahertz work, then you're able to see the world with new eyes that MRI and X-ray modalities cannot. That's it.
Okay, thank you, Rob. Our next speaker is Robka.
Так. Oops. I am waiting for Rob. Sorry.
Be able to share. I'll stop.
Can you see me?
Yep.
Yeah.
Okay. Good morning, everybody. My name is Xiao Dongchen, and I'm presenting, maybe not so big, but enhancing harmonic beat tracking radar performance presentation. Oops. Sorry. We work together with School of Biology, Chemistry Sciences. This project was going for several years in biology department, and the main aim of project tried to track bee behavior, and it's important for understanding more deeply how they operate. And existing radar system which was developed in during the project unfortunately didn't show perfect results, very good results, and especially in terms of changing 2D system into 3D system. In order to improve characteristics of radar, new digital signal processing procedure should be developed, and well, there were troubles with antennas, and actually our work was to enhance performance of this 3D harmonic radar, trying to change antennas and improve digital signal processing. System worked quite simply. There is a transmitter at 9.4 gigahertz. After that, signal received by tiny antennas installed on bees, and with the help of small multiplier or nonlinear element which is incorporated into this antenna, signal retransmitted at higher frequencies and second harmonic 18.8 gigahertz and receive, and we can track behavior of the bees real time. When you start this is the original system in the left bottom corner. As you can see, this LNB block, which has 5 channels, is creating a lot of obstruction for transmitting, or sorry, receiving signal. And on the right, you can see radiation pattern of such system, and red, especially, you can see red curve has a deep in the middle, and channel 2, 3, 4, which is we have 5 channels altogether to control our 3 elevation angle of the B under the interest at the moment. As you can see, red color has the same level as two others, and it's very difficult to distinguish and use these signals for further digital signal processing to find out position in elevation. So it was done, we suggested to change the system with minimum expenses from prime focus system to offset system. And as you can see on the right, this transformation could give us 5 clear radiation pattern, which 5 clear channels, and it should decrease ambiguity of received signal and of course improve behavior of system at all, and makes much better and simpler digital signal processing. Digital signal processing, which was done by a group of Khalid, Rajab, and I don't know if he can join us now. If not, I just say quickly that channel responses, as we saw in the original system, were not consistent. Calibration, we have to do some calibration. We have to improve antenna system, and we found how, and it's kind of very not expensive solution. And I show you a small video how you can see 5 channels, and our radar, like in the airports, scanning 360 degrees. And we can see responses in azimuth position from based in there. As you can see, 5 channels showing approximately the same position of southwest. As far as we have access to complete these measurements and to improve system, because of COVID, we cannot do it in field. We hope that the system will operate properly as a nice 3D radar and give us, our colleagues in biology department, good chance to enhance their research. Thank you very much for your attention.
Okay, thanks, Rossi. Our next speaker is Dongchen.
Stop share.
Good morning. My name is Xiao Dongchen, and I'm talking about a large compact antenna test range. Actually, this is a quite a historical research project in our group. So, a compact antenna test range is only practical technique for testing large antennas in millimeter wave and terahertz band. And for example, in 2009, ESA has launched space telescope. One is called Herschel, one is called Planck. The Herschel has a large antennas of 3.5 meter diameters, operating frequency range of 450 to 5 terahertz. And Planck has a smaller antenna, still is 1.5 meters diameter, operating from 30 to 857 gigahertz. So to testing all these antennas, the only feasible way or practical way is using compact antenna test range. And this technology has been developed in our group for a long time. And so around the 2000 millennium, Clive, Rob, and a few other colleagues developed a tri-reflector compact antenna test range and try to develop, improve the white zone efficiency. Originally, for single reflector, efficiency is only 30%, and the tri-reflector is 70%. and prove the concept building a prototype. And the operating frequency going up to around 325 gigahertz. And this idea somehow get getting cold because of lack of funding. So around 2004, 2005, we set up a joint lab with Beijing University of Post Telecommunications, and we found there is funding source available to push this idea further into sort of engineering realization of a compact antenna test venue in high frequency band. So in that collections, we have tried to push this reflect test range up to 500 gigahertz, and also make the quite much bigger reflected 3 meters. So sort of new improved configurations using parabolic main reflector. Used to be spherical reflectors, and also changing the configurations, and also using this B-spline shaped subreflectors. So we managed to push the quad zone efficiency over this range from 80 to 92%, almost reach the theoretical limit, and also have very low cross polarizations. So this is a design or simulation result, looks quite encouraging, promising. And this project going through the 2 phases. Second phase is sort of engineering implementation is going on. So the main reflector will be built by 16 panels, and also we have this feed and subreflector subsystem being manufactured by Thomas Keating Limited, and also we build a huge chambers, still not as high as the current one at Canary. It's 8 meters high, and to host this compact test range. So original plan was to finish it by the end of this year. Due to the virus pandemics, probably sometime next year. Thank you.
Thanks very much, Don. Our next speaker is Henry Goodens.
Hello, I'm Henry Goodens and I work at Queen Mary University in the research group of Professor Yanhel. Today I will briefly introduce some of our work looking at 3D printed antennas spanning frequencies from microwaves up to terahertz. Over the last 10 years, the cost of 3D printing has drastically reduced, and a number of printing techniques are readily available off the shelf from a wide range of suppliers. Our researchers look to take advantage of these factors to produce both low-cost and novel antenna and electromagnetic devices. For example, on the left-hand side, we can see the permittivity distribution of a classic Limburg lens, a device which converts a spherical wave emerging from a point of one of its surfaces to a plane wave propagating through the other side. Such devices have been known about theoretically for decades, but were previously rarely used in practical applications due to difficulties in realizing the spatially varying material profile. 3D printing allows us to easily fabricate such devices. The radiation pattern measurement at 30 GHz shows how the lens produces a collimated beam in any direction. Taking inspiration from these types of devices with varying material profiles, we have designed graded index lens antennas using multi-material 3D printing for military man radios at 5 GHz, along with some industrial partners. The lens antenna on the right-hand side, which has 8 different segments and a switch feeding network, is able to radiate with optimized radiation patterns in any of its 8 segments, or with a multi-beam pattern when each feed is excited simultaneously. Moving up the frequency spectrum to millimeter wavelengths, we have demonstrated a number of designs inspired by the group's previous research in the transformation of optics under the Quest program. Here on the left-hand side, we can see a compressed Limburg lens antenna operating across 80 to 100 GHz. The antenna requires a material profile with permittivity ranging from 7.5 in the center to 3 on its surface, and is able to produce 20 dB of gain with a steerable radiation pattern dependent on the position of the feeds. The lens was realized using specialist dielectric filaments and multi-material 3D printing technology, which allows us to use up to 5 materials in the same design. The same multi-material 3D printing techniques were recently used to realize a steerable terahertz lens antenna, where we demonstrated a terahertz comm system with 40 gigabits per second data rate at angles of over 20 degrees. We're continuing to develop our 3D printing capabilities by utilizing the unique facilities at Queen Mary, including a nanoscribe printer for lens antennas up to 500 gigahertz. We're also developing antenna systems for 5G applications and automotive radar. Thank you for your time, and if you have any questions or are interested in this work, then please feel free to get in touch via the emails shown on the slides.
Thanks very much, Henry. Our next speaker is Jijin Qin.
Sorry, I was muted. Hi, this is Jijin. I'm going to talk about the symmetric communication systems. So based on the channel and the winner, the communications could be categorized into 3 levels. First level is about the transmission of symbols, as we could see from the current communication systems. As we could see from the current communication systems, such as 4G and 5G, the capacity of it has been well developed, and the capacity of it is, the system has been well developed, and the capacity is approaching the channel limitation. While the second level of communication deals with the symmetric information sent from the transmitter and the meaning interpreted by the receiver. We call it symmetric communication, which could potentially improve the system efficiency significantly. For example, I have a sentence to transmit. I have for automobile. By using the symmetric communication, I could interpret the sentence as I own a car, even when the channel condition is quite poor, in which case the typical communication system will not be able to recover the transmitted symbols or means. By using the symmetric communication, the information redundancy will be removed in symmetric domain. By doing so, the features and action networks will be also considered in the design of the communication system. In that case, only the useful and relevant information will be transmitted to the receiver. In the past decades, many researchers has started to investigate the symmetric communication, but the progress is very limited. This is mainly due to the lack of mathematical models. But due to the recent development on the deep learning, the symmetric communication could be investigated and realized without requiring a mathematical model. So to realize the symmetric communication, we have invented a model called DeepSC, which jointly designed a symmetric encoder and a channel encoder to support the successful transmission of symmetric informations from the texts. The simulation has showed that the DeepSC could achieve higher blue score, especially when the SNR is low, which means the receiver, the symmetric receiver, could interpret the meaning of the transmitted sentence properly when the channel condition is quite poor. The DeepSC could also reach higher system capacity compared to the typical ones, and it is also adaptive to dynamic environment quickly. So here are the 2 papers we have published in the related area. Okay, that's all for it. Thank you.
Thanks, Jijin. Our next speaker is Kamiyah Mehran.
Hi everyone, I'm Kamiyah Mehran, Senior Lecturer in Electrical Power Engineering based on Antennas and Electromagnetics Research Group. Today I wanted to talk about my research on multiphysics modeling for the reliability monitoring of the wide bandgap power electronics in electric vehicles. Power electronic components can be used as bidirectional charges for the batteries to convert or transfer the energy from the batteries to the electric motors, which is running the wheels. With the modern electric vehicles, the electrical systems must be designed in such a way that it can tolerate electrical stresses and overheating and sudden loading. At the same time, the power electronics components has to be smaller and the power density has to be higher. So we use materials like silicon carbide or gallium nitrides in modern power electronic switches to boost the power density, simplify their constructions and reduce the cost, and increase the thermal reliability significantly. One of the major challenges caused from thermomechanical stresses or cycling in electric vehicles, which can make the interlink heat transfer on power modules very complex and can end up in bar-1 degradation, solder cracking, and delaminations of the power semiconductors on the power modules. Today, we can measure the junction temperature of the silicon-based power semiconductor using temperature-sensitive electrical parameters or TSEP approach. But this approach cannot work for silicon carbide-based devices due to the really low power losses and the high frequency, normally above 20 kilohertz, which just end up in a conduction noise and measurement errors. We use non-intrusive early detection, which is the beyond the state of the art. Using the current density measurement across the modules, we thermally characterize the thermal distribution over the whole module, including the junction temperature of the devices. And then we build a multi-physics model that can electrically, magnetically, and thermally represent the device. And using this model, we can also find out the material degradation in the devices. The condition monitoring system can predict the failure rate on the power modules in real time and can be used on board on the electric vehicles. You can see some results of the multiphysics model, which has shows as a 3D, the temperature distribution across the modules, included junction temperature of the power semiconductors. At the same time, you can see the flux density distribution on the whole board. Using adaptive control methods, our condition monitoring system can adapt itself in the long term and can better predict the failure rate in the power modules. Hi everyone, I'm Kamiyah.
Yeah, you don't want to do it twice. Okay, and our next speaker is Sergey Lopio.
Hello? Yeah, can you see the presentation? Yes, perfect.
Yep.
Hello, this is Sergey Lopio. Today I'm going to talk about iSpace science at Felix Laboratory, which is a large facility in the Netherlands, an EPSRC facility. So with iSpace science, I mean the study of the formation of molecules in space. We know that molecules in space can be formed in the gas phase, but perhaps the most complex and life-related molecules are formed on top of the surface of dust grains in the solid phase. Those dust grains and the ice that grows on top of it and all the gas around it then eventually lead to is used for the formation of stars and planets. And so understanding the chemistry and physics that happens in space also might lead to our better understanding of how life was formed on Earth and perhaps elsewhere in the universe. So here on the right side, you see the evolution of interstellar ice grains. They start growing on top of this bare ice, dust grains, and the first layer is a water-rich ice. And then you can see, following this scheme here, you see that actually the complexity of those ices increases with time and evolution of this object that lead to the formation of stars, planets. Water is the most abundant molecule in the solid phase in these ices, but we also know that more complex molecules are formed through energetic processing, which mean electron irradiation of these ices, photon irradiation in the UV, but also through cosmic ray irradiations and shocks, but also atom addition reactions. So it is a very complex problem to solve, and people try to tackle it by remote sensing, so detection of these molecules in space, but also using laboratories, facilities, and computer models to simulate the conditions in space. So what we need to do from the laboratory point of view is to expand our laboratories and move them to large facilities. In this case, I'm going to talk about the free electron laser facilities, Felix laboratory in the Netherlands, which is also, as I was saying, an EPSRC facility. So there is a larger UK contribution in it. And the reason why we want to move space science there is because we can use the unique capabilities of free electron lasers, which are mainly the wide tunability of the laser, the high intensity, and the fact that it is a pulse laser, so we can actually do pump-prop systems to investigate complex problems such as the formation of molecules in space. There I build an end station called LISA, which simulates the conditions in space, and I can reproduce those under laboratory control conditions. What I've been doing there in the past few years, apart from building the system, was also to investigate how energy is injected in these interstellar ice analogs. And I started working with water ice because it is also the most important, most abundant species in the space, but also it has a very interesting structural dependence according to whether it's deposited at very low temperatures, typical of dense clouds, and is an amorphous material, or at higher temperatures that becoming a crystal. So injecting in energy at the frequencies in the infrared or in the terahertz might lead to structural changes in the ice. And I studied that as a function of the frequency with this laser. But I also host different external groups at the facility that study the diffusion of molecules in these ices, or also the desorption of molecules. So all these physical chemical problems there. So showing you what I've been doing there. Here you see basically that the infrared spectrum of the water ice, pure water ice, amorphous, that has been processed with an infrared laser. And we saw that by looking at our experiments and computer simulations, molecular dynamic simulations, we saw that actually the process of energy injection is frequency dependent, because the ice can absorb energy only at frequencies where actually is allowed to absorb this energy. And the effect that we see is crystallization of the ice, so an increase of the OH network. And what we want to do next is to move from this saturated effect into studying more of the transient effects and exploring the capabilities of these lasers of being pulsed, so generate systems that are time resolved. And for that, we're going to use the antennas group, laboratory, the terahertz time domain group, and collaborating with that and Felix, we are going to expand the capabilities of these experiments at free electron lasers. Thank you.